Welcome back to the session on subscript notation. So, in this session we will be looking at one more quantity epsilon and then how we can combine the Kronecker delta and epsilon to make some of the derivations. So, just a brief review of the subscript notation or the so called Cartesian summation convention. These are the 5 rules that we were using in the previous session. The first rule is that the subscripts that are repeated are called the dummy subscripts, and you can also call them as indices. So, the dummy indices should be summed up over the range that the subscript can take, which is basically from 1 to 3, and the subscripts that are not repeated are called the free subscripts or free indices, and subscripts can come in the numerator or in the denominator, and if there is a comma, then it means that the subscript that follows the comma is the distance variable with respect to which we are going to do the differentiation. And we have to verify that every term on either sides of the equal to sign should have the free indices that should match. The dummy indices in each term need not match because they are going to be summed up anyway. So, here we are getting ourselves familiarized with a new symbol, that is the epsilon symbol. This is called the Levi-Civita symbol or the permutation matrix. Now, we will see the meaning of this epsilon shortly, but for now let us look at the subscript notation that has been used here in these 3 terms. So, how many terms are there in the following expression? So, let us take the first expression. You see that in this expression the indices j are matching and also k are matching. So, the I is the only free index, and which means that there is one free index. So, 3 raised to the power of 1, that is there are 3 terms. In other words, what we wrote was basically a vector, and if you want, you may want to call this as w. And what index should I choose for w? So, it is clear that the free index on the right hand side is I. So, you would call this as wi, which is also basically a vector w. Okay. So, we have used epsilon as a symbol to change the indices of u and v into the index of w, and there must be a relationship between the 3 vectors u, v, w. What that relationship is will be evident a little while from now. Look at the second expression. In the second expression we are using a differentiation because there is a comma out here. I bring your attention here, there is a comma, and k and j are repeated. So, again is the same thing as earlier. I is the only free subscript, and therefore, we have got the same expression. You could have some other vector w with a subscript I, which is the free index on the left hand side as well as on the right hand side. The third expression, if you see, the 3 indices are all matching. So, if you see the first index I is matching with this, and then j is matching here, and then k is matching here, which means that there are no free indices here, which means that this will have only one term because the number of free indices is 0. So, 3 raised to the power of 0 is 1. So, there is one term, and what does this symbol mean will also be evident shortly. So, here we are using the epsilon symbol, and I am giving you the meaning here. As you can see, epsilon as a symbol, if you want to look at, it has 3 free indices I, j, k, and how many numbers will be there in that. So, you now know that it should be then 3 raised to the power of 3, and that will be 27. So, there are 27 numbers that will be represented by this one symbol epsilon, and out of these 27 we can see that 3 of them are 3 terms or 3 symbols are basically +1, and then 3 of them are -1, and the rest 21 are zeros. And these 3 values are when the subscripts of epsilon I, j, k, if they are cyclic, then it is 1, if they are not cyclic, then it is -1, and if there is any subscript that is repeated, then we have that as 0. So, individually all the elements have been listed in these relationships here, and we can see that there is a special property of epsilon, which is why it is of course called as the permutation matrix. The property is as follows: whenever we have the subscripts that are cycled, then the value does not change, which means that when you look at a symbol like this 1, 2, 3. So, you take 1 and put it on the other end and you see it is 2, 3, 1, and these two are basically the same value. In our case it will be 1. So, even when we are using subscript notations where the indices are not expanded. So, the property of epsilon we are going to illustrate here. So, let us say in any term you have got I, j, k, then you could take the I onto the other side and write as follows. You could write it as epsilon j k I, and then again you could take this term to the other end and you could write it as epsilon k I j. So, all these three are cyclic variants of the three indices I, j, k, and you could substitute one with the other and they are all the same as far as the subscript notation is concerned. So, this special property, which is why we call it as a permutation matrix, will be very useful when we are doing some derivations in the later part of the session. So, this symbol is then formally to be defined, and we could define it as a triple product of three unit vectors which form basically the unit vectors of the axis that you have chosen. So, x1, x2, x3. So, if there were these three unit vectors, then the volume of the cube formed by these three unit vectors is what is given by epsilon I, j, k. And as we can see here, if there was a repetition of the index, it means that basically the dot product will give you 0 and therefore epsilon will take a value of 0. And if they are cyclic, then we are using the right handed system, so you get +1, and if they are not cyclic, we are using a left handed system which will give you a -1 for the value. So, you could think that Levi-Civita symbol is nothing but the volume of the unit cell, and with the three indices denoting the three unit vectors that are forming the cubic. So, now let us make use of this symbol to make some derivations. So, here the way we have to understand is to pay attention to the sequence of the subscripts. Unlike in Kronecker delta, where if you swap the two indices, it does not make any difference, here it makes a lot of difference. For example, when you wrote a symbol like this delta I j, you could as well have written this as delta j I, because they are both the same value. Okay, for a given set of numbers for I and j, they both will have the same value. In other words, this is symmetric over the indices I and j, whereas when we write epsilon I, j, k, the sequence of these three must be very important. So, we will illustrate how we are going to use this in our derivation as follows. Okay. Here, let us take the curl of a vector u. So, here we have got the curl of vector u, which is given by the vector p. So, the way the curl operator is going to translate in the subscript notation is as follows. We know that operators can also be given a subscript. So, in this case the operator is given a subscript j, and the vector has to be given a subscript, so that is given k. So, we write the subscripts for epsilon in such a way that the second one corresponds to that of the nabla operator or the del operator, the third index corresponds to the vector. So, here I would illustrate it here like this, epsilon I, j, k, and then you have got del j and then u k. So, it is very important to get this right. So, this is how it goes. Okay. So, this way we will not make a mistake, as we know that when the rotation axis is different, then you get the sign changed in these kind of vectorial operations. So, keeping the sequence correct is important. So, when we expand the nabla operator, we know that this is nothing but this kind of a thing. So, then you expand it here, and then you could then use the comma symbol and write it the same way here. So, which means that the curl operator is then expanded using the epsilon as follows. So, whenever there is a curl operator, you could then immediately use epsilon and then you can make a subscript notation of the entire symbol here. And the output is basically a vector. So, which index should we use for that vector? It is already known to us, because when we look at this expression, you saw that the j is repeating and the k is also repeating. So, the one which is free index is I, and that should be the index for what is supposed to be here, okay, on the left hand side. So, p of I is equal to, so this index has to be shown such that we do not have a violation of the subscript notation rule, the last rule which says that the free subscript should be matching on both ends. Okay, so, cross product and the curl operator are to be treated in a very similar manner. So, the way you write a cross product is very similar. Instead of the nabla operator, here you are writing for the vector u and vector v. So, here also the same rules apply. You could see that the second index is used for u and the third index is used for v, and the free index which is there, which is I, is what is used for the outcome p. So, p vector p is nothing but a cross product of vector u and vector v. So, the indices for u and v, if you decide them, then you could immediately see what should be the index of p, okay, and epsilon having the 3 indices will immediately give you how the notation has to be written. Now, this is going to be used again and again later on. So, getting the sequence of these indices is very important. Okay. So, now there are some direct usages of the permutation matrix which are evident from the very definition. So, we can see that from the definition we can use it to know whether 3 vectors are coplanar, and this condition shows how to evaluate that. It is evident that when I, j, k are correspond to the indices along 3 perpendicular axes, then you get the volume, and if they are repeated, which means that you get 0. So, it is very obvious that when they are repeated, it means that the vectors are actually being in the same plane, and therefore, you get a 0 there. So, this is a direct application of the permutation matrix from the definition. Another interesting quantity that we came across earlier is this quantity. Okay. So, when you expand it, you basically have 9 terms, because this is nothing but, so I is equal to 1, 2, 3, j is equal to 1, 2, 3, k is equal to 1, 2, 3, and then epsilon I, j, k, a 1 I, a 2 j, a 3 k. So, if you expand this and knowing that epsilon has values like +1 and -1, you could immediately see that this must be something to do with the determinant, and if A were to be a matrix, then this gives you the determinant, and this actually allows you to write programmatically how to evaluate the determinant once the matrix epsilon is already available to you. So, these are the simple usages of the permutation matrix. We will see how to use it to actually prove some of the vector identities as we go along. So, here are some identities that I am writing. So, this is a practice to check whether we got the symbols correctly. So, C, which is a cross product of A and B. So, I am just repeating the concepts once again, so that we are practicing the subscript notation. So, here we can see that if I want to give the indices of A and B, then that of C will be I, and here that is how it is, and you can see that the second index is matching that of A, the third index is matching that of B. So, the remaining index, which is the free index, that becomes the index of C. So, similarly we can write it for the curl product. Here also we have seen that the j is matching here, and then the k is matching here, and then the remaining index is here. Now, whenever there are multiple operators like dot and cross, then we must then combine the rules that we have used for Kronecker delta as well as the permutation matrix. So, what is the rule for the dot product? The indices have to match. So, that is the idea of dot product. And what about the rule for the cross product? Epsilon will come into the picture. Okay. So, we are going to use that concept. Let us look at the del cross A. So, because it is a cross, then I want to use the indices in such a way that I get a I index free. So, I will put a j here and I will put a k here, so that when I have epsilon I j k dou by dou x j a k, then I got this term covered. Now, the free index of this expression, which is written here, the free index is basically I. So, I must use the same index for C, and that is how I write the dot product as C I epsilon I j k dou by dou x j a k. Now, once we write like this, then we realize that epsilon being just a number can be just brought in and out of the expressions. So, that is why we bring it out, and then we can write the expression as follows. We can write it as epsilon I j k C I dou a k by dou x j. So, you can see that an expression like this here can be written in this form. Okay. So, whenever there are multiple operators, like there are two cross operators, then we basically will require two epsilons, which means that we will require two sets of 3 indices, and we have to then judge very carefully whether we will pick them in the correct order. So, let us look at that here. So, the very first symbol I am going to write here is here, this one. So, I want to write it as S and T, and I use epsilon RST as the first epsilon, and then you can see that the free index of this part of the expression, the free index of this part will be then R. Okay. Now, if this was R, then I can choose this index of the C to be Q, so that the free index that is coming out for whatever is the output is the P. So, that is why I write here epsilon PQR, then CQ, then epsilon RST, then dou by dou x S, and then AT. So, we then use the idea that we could actually move epsilon in and out of the terms. So, we can write the expression in this manner. Okay. So, here I just repeat once more. You can see that CQ and RCQ, these symbols, if you see how many are repeated and how many are free, you could see that Q is repeated, you could see Q here and here, R is repeated, S is repeated, T is repeated. So, the only index that is free is P, and which implies that this must be a quantity which is index of P, which I may want to call it as vector D. So, if I want, I could write this expression as is equal to dP. Okay. So, then you can see that you can write the expression in this manner. Now, there are 27 values of epsilon, and there are 2 epsilons sitting side by side. So, when I want to expand this, then is there any shortcut that is possible? Yes, there is a shortcut. So, whenever there are 2 epsilons, then you can expand them as Kronecker deltas, and that will be there in a slide from now here. So, whenever there are 2 epsilons, this is what you do. Okay. So, when there are 2 epsilons with only one index matching, what we do is that we take the other 2 indices and make them into 2 pairs, and this expression is then an identity. By identity I mean it is applicable always, and how to verify? So, for each combination of ij and lm you could verify, and that is going to be quite tedious because you have got 81 combinations that are going to come. Nevertheless, you could just pick a few of them and then verify whether it is true or not. So, this expression when you want to write, you would see on the left hand side you have got epsilon I j k epsilon k l m, and this is nothing but basically k is equal to 1 2 3, and this is basically for each I j l and m. Then you have got for each value of I j l m, you are summing up 3 pairs of epsilons and then getting the value, and these are the values that will come out. And this expression is very useful because of the property of Kronecker delta. We already saw the property of Kronecker delta. I am just reminding you that property here. Whenever you have got any expression A I j, and then it comes in beside Kronecker delta with indices that are matching, let us say j and l, then we saw that the property of Kronecker delta is such that whichever index is matching, then take the other index and then put that in its place. So, which means that this must be A I L. Okay. So, Kronecker delta is going to be helpful in reducing the number of indices, and then whenever there are 2 epsilons, it can be converted into Kronecker delta, which means that while working with these expressions, even if you have many epsilon terms coming in, there is nothing to worry, because eventually they will be converted to Kronecker deltas, and which then reduce the number of indices, and then we will retrieve the quantities that we want. So, these are going to be used in derivations that I am going to detail now. So, we can now practice some derivations of vector identities to see whether we can use the subscript notation to reduce the amount of algebra. So, as we go along, we will see the benefit, and here I am starting with a very simple example. The first example is essentially to prove that this is true. Of course, you can visually inspect and say that this must be true, but the way we do it in subscript notation I am illustrating here. So, this is essentially to guide you to do the derivations further down. First, what we do is we take the left hand side and then write it in terms of the subscript notation, and so the nabla operator is going to be written in this form. And then once this is over, what we do is we differentiate by parts, because this is a differentiation operator. So, when we differentiate by parts, first you can take the psi out to differentiate phi, and then take the phi out, differentiate psi, and then we realize that we have got terms that we can again bring back into the vectorial notation, and that is what we have done here. So, we can see that in one step we can actually derive this. Of course, there is not much complication in this kind of a derivation, but you can see that the subscript notation can be used to reduce the algebra. If you were to prove this by using different components of the nabla operator, then the algebra would be a lot more. Okay. So, let us talk with some more operators that will come in as we go along. So, here is an identity that we must now prove. There is nothing much to prove, because we are actually going to define an operator del square here. So, what we do is we write the left hand side in terms of the expansion of the operators nabla, okay, which is nothing but dou by dou xi, and then when they come twice, then we can differentiate twice, and that is what is this. And we are now defining this operator nabla square, we are defining it as this kind of an operator. Okay, once we define, then the right hand side has been arrived at, and therefore, the proof is here. Now, we are going to use this definition in some of the derivations later on. Okay. So, here is a derivation again to show you that the curl of a grad of a scalar function is 0. And this can be proved as follows. Whenever you have got something like that, you know that it is a vector, because phi is any scalar function, and then the del operator is basically giving you a gradient. So, that must be a vector. So, that vector should have some index. Okay. So, we are going to assign some index, and the index that is assigned is k. Okay. And you have got one operator here, you want to use an index for that, and we have chosen the index to be j. So, we choose the ijk as the cyclic sequence of indices. So, the remaining index is I. So, that must be what is for the quantity that we are actually expressing in this form pi. But then what happens is that we saw that you have got a combination of two terms, one is epsilon ijk, and then other is dou square phi by dou xj dou xk. Now, there is a certain property of differentiation whenever phi is well behaved. Okay. So, we assume that it is a scalar, it is a scalar function that is well behaved. What we mean by well behaved is that whenever you change the order of differentiation, then there will be no difference in the quantity that is coming out. So, what it means is that when you take, for example, the p and look at one of the terms p1, then we see that when we expand pi with I is equal to 1, on the right hand side, then you see that there are two terms that are coming here, and then you could then sum it up and you get epsilon 1 2 3 plus epsilon 1 3 2, and I am equating these two because I differentiate first with x3 and then x2, or first with x2 and x3, it does not matter, because we say that the order of differentiation should not matter. So, we are going to use that to take that as common, and that is what is taken as common here, and therefore, we can sum up these two epsilons, and then when we saw these values, one is plus 1 and another is minus 1. So, they will get a 0. So, which means that we are actually now discovering something very interesting with respect to the symmetry. The idea is as follows: this quantity is called as symmetric over the indices j and k, because when you swap the indices j and k, the quantity does not change. Similarly, this quantity is called asymmetric over indices j and k. The reason is that when the values of j and k are swapped, then you get a negative value. So, which means that you are now doing a summation. First of all, let us see pi. Pi is actually a summation. We see that pi is nothing but j is equal to 1 to 3, k is equal to 1 to 3, epsilon I j k, then dou square phi by dou x j dou x k. So, it actually is summation over the indices j and k, and we see that when we are summing, we are seeing that there is a symmetric part and there is an asymmetric part. The asymmetric part is going to change the sign and the symmetric part does not change, which means that when we sum, like here, we get zeros. So, we are going to use this property later on in many of the derivations. Whenever we see an asymmetric form of a quantity coming in contact with a symmetric form, and then when you are going to sum up over the indices over which the symmetry is differing, then the sum will be 0. So, we do not need to then expand all these terms to decide on what is the magnitude. Visually we can see whether the symmetry and asymmetry are coming together. If they do come together, then we will immediately assign that quantity as 0. Okay. So, now there are some more relationships that I want to just summarize here, so that when we are deriving the vector identities using subscript notation, then this will be of use. So, we have already come across this. One is the coplanarity, and another is whenever you have got two epsilons, how to convert them into Kronecker deltas, and then we have got also whenever there are two contracting indices, what will happen. So, you have seen that here I and j are common and k and m are the free indices. So, you could see that you get a quantity that is similar. So, these two identities are going to be used in the derivations as we go along. Okay. So, we are going to have about another 5 more derivations. So, we will go through them, and I will only highlight the points that we are making use of instead of narrating how the derivation is done. So, this is the quantity that has to be derived using the subscript notation. So, we start with the left hand side and we expand it using the subscript notation, and then the differentiation by parts we expand and then write, recognizing that when the subscripts are matching, then this must be the dot product, and then when you have a scalar quantity with I there, then it must be a grad. Okay. And then the subscripts are matching here. So, that is the reason why we have got a dot product there. So, subscripts are not matching here. So, that must be the dot product here. So, this is how we write the expression given here in terms of the subscript notation, and then using the differentiation by parts, we can then immediately see that the outcome is on the right hand side. So, we could see that the RHS is coming out just by only one step, namely the differentiation by parts. So, there is only one step derivation in this kind of a equation. So, there will be multiple steps in quantities that are of more complexity. So, here we have got an expression that has to be derived using the subscript notation. So, we start with the left hand side and we have a curl here and there is a vector here. So, we choose the subscript for f to be k, subscript for the first operator Napner to be j, so that the free subscript is I. So, this is some quantity I, okay, and then we can write the expression here, and once we write, then we recognize that the differentiation indicated here has to be acted upon two terms, and therefore, we do it by parts. So, when we expand, then we get this expression here. So, let me indicate this by parts is going to come here. Okay. Now, we multiply epsilon with each of those, and we could take epsilon in and out, and that is what we are doing here in the second term, and then we realize that quite straightforward, we could see that you have got a j here, you got a k here, and then there is an epsilon I j k. So, there must be a cross product, and here also we have got a j here, we have got a k here, there must be a cross product, and we can write the final expression straight away. So, in about 2 steps we are able to derive. So, imagine trying to derive this vector identity using the components of f, components of the nabla operator. So, that would be a lot of algebra which is now saved because the summation convention is making us save the space. So, one more derivation, which means basically the divergence of a curl of a vector is 0, and that can be derived using the symmetry properties that we discussed earlier as follows. So, we have now the task here, you need to decide on the indices. So, I will choose j and k for the indices here. So, what would be the free index that will come out of this quantity? That would be the I, and therefore, I should choose the same index here. Okay, so, that is what we do. So, we choose I here, and then the j and k I choose here, and then I get this term. Now, immediately we see that in this term we have got the same symmetry argument. I and j are basically acting on f, and so for each component of f vector, if each component is a well behaved function, then the differentiation order does not matter. So, this part is then symmetric over I and j, and you can see that this part is of course asymmetric, and then you can immediately see that this must go to 0. So, this is how you could then prove that this identity will take you to 0. Okay. So, one more derivation here, which then is a little bit more complicated because we have got more terms, and we can see that this can be also done in a very straightforward fashion. So, we start with the left hand side, we have the left hand side, we decide the indices. So, let us decide the subscript for f as j and the subscript for g as k, and then there is a dot product. So, I must have the same index as what is remaining from epsilon. So, if epsilon has ijk, then I is remaining. So, that is what is in the index I will put here, and then this is what I get, and then I take the epsilon out, and then I have then a differentiation by parts coming up, and that is why you have got 2 terms here, and then we multiply term by term, and then here there is some small manipulation I am doing, which is basically the idea about the cyclic nature of indices of epsilon, which should not change the quantity. So, what am I doing here? So, what I am doing here is I will highlight here, you can see that I have changed the order of indices. Why did I change? The reason is that the indices are here k and I. So, I must have I as the second index and k as the third index. Similarly, here I and j. So, I must have I as the second index and j as the third index. So, that is the reason why I am cycling the indices. So, epsilon ijk I have cycled that as kij, and then it matches quite well. You know, the second index is I and it is matching here, the third index is j, it is matching here. But when I try to do the cyclic rotation of the indices for the first term, then you can see that the sequence is not matching, which means that this quantity should be negative of whatever is a cross product, and that is the reason why from here to here when we go, we introduce a minus sign. So, jki, jik, I am swapping the last 2 indices, and therefore, I put a minus sign. The moment I do swapping of indices, then I see that the second index is I, third index is k, second index is I, third index is k. So, then I can write this quantity as del cross g, and that is what exactly what is done here, del cross g. The minus sign is coming because I did the swapping of last 2 index, and that is the minus sign that is coming here, and the first term is shown here, and you can see that this term is matching with this term, because you could see that kij dou fj by dou xi is nothing but del cross f, and then k is the free index, and you are dotting with the g there because the k is matching there, and therefore, it is g dot that. So, you can see clearly that proving this vector identity has involved 2 concepts. One concept is the differentiation by parts, and another concept is the cyclic nature of the indices of epsilon. So, these 2 are basically conventions of the summation convention, and therefore, by using the subscript notation, we have made the differentiation very simple, and in about 2 or 3 steps we have got this identity proven. Okay, one more such identity, this is a bit long one. Here we are going to make use of the identity that involves 2 epsilons. So, this is the identity that we are supposed to prove. So, what we do is that we do not start with left hand side and go to the right hand side. What we do is that we start with this term and see if we can get the remaining 2 on the other side. So, curl of f is going to be written. So, first we will write curl of f, and here we write here with the indices as follows. We take the index for f as k, the index for the del operator as j. So, the remaining index is I. So, I is coming up as a free index. So, for this quantity the free index is I. So, then I must then have another 3 sets of indices in such a way that they are also cyclic. So, I choose them as Lm, and therefore, then I could then choose this as I. So, then here I would take m, and therefore, I could put an epsilon Lmi here. So, the m corresponds to the operator here, the I corresponds to the remaining index here, and then I have got this term written. Now, once we have written here, then we can take the epsilon out, and therefore, we have got the epsilon out here, and the dou operators are coming together here. Okay. Now, once we have got 2 epsilons, we have already had an identity that will convert that into 2 Kronecker deltas. So, that is what is expanded here. So, what is the common index? I. I is the common index between the 2 epsilons. So, j k l m are going to be used here to expand, and the other term is left as it is. So, in the next step, we can then see how it has been simplified. The way it is simplified is as follows. We then basically multiply each of these terms and separate it out. So, here we are going to use the property of Kronecker delta in reducing the number of indices. So, we could see that how we are doing it. So, you could see that the first we see that the index k is matching. So, the m should go there, okay, under f, okay, that goes here. Similarly, here, okay, so k is matching. So, this other third index has to go here. Okay. So, this is how we have reduced the number of Kronecker deltas from 2 to 1, because we have used one of the Kronecker deltas to change the index. Now, once we have changed, then you can use the other Kronecker delta again to change further. So, that we have done here. You could see that the j is matching. So, we bring the L into that, okay, and similarly here also you could see that j is matching, you could bring the m there. Okay. Now, that is why you got 2 m's as the subscripts here, because one of the j's has been substituted with m, because that is a property of Kronecker delta. Similarly, here dou square f m by dou x m dou x l, because j has been removed and l has come there. Now, you have got these 2 terms which can then be expanded further, and it is very easy to see that from here to here, what we have done is we have swapped the 2 terms in the denominator, dou x m and dou x l, we have swapped. The reason why we swap is because of the property that the order of differentiation should not matter. Okay. So, once we swap the indices, then we recognize that the term that is coming out is with the same index, and that is nothing but the dot product. Okay. So, whenever you have got the same index coming in the denominator and numerator, that is nothing but the divergence operator that we have done earlier. So, that is what is going to be used here, and similarly the other one will nothing but denominator is coming twice. So, we have already defined this as the operator del square, and that is we are going to be used. So, this is how we have then found that the derivation here we have got this term and this term coming out, and this has been proven here within just 3-4 steps. So, what are the concepts we have used in this derivation? We have used the concept of what happens when there are 2 epsilons, how that will be used to convert into the Kronecker deltas, and then how a Kronecker delta can be used to replace the subscripts, and how the order of differentiation can be used to swap the indices, and then how we can then sum it up with the operators that we have defined earlier. So, the vector identity derivation can be quite simple, okay, using the subscript notation. So, one of the last of these few derivations that I am illustrating to you here. So, this is the last derivation. It appears quite formidable, because if we attempt this kind of a long expression using the various components of f and g as well as that of the Nabla operator, then it is going to be a mammoth task keeping track of all those terms. So, there are a lot of terms that are going to come in, and we may make algebraic mistakes as we go along in deriving. but when we choose the subscript notation, we can see that the amount of algebra is quite limited, and therefore we can do it quite correctly. So, I want to illustrate that here now. So, let us take the left hand side and choose to have the indices as we want to. Okay. So, we choose them as j and k. So, f j and g k. Okay. So, the reason is that epsilon I j k. So, this term I want to use an epsilon, so that the I part is then coming out free. So, if the I part is coming out free, then I can then choose that as one of the indices for the next nabla operator. So, I would then choose that here. So, this is the first thing that we have written, I is the free index. So, for this term I is the free index. So, then I want to use another one. So, I could then use this fellow as m, and then the L will become the free index. So, L is the free index that is sticking out. Okay. So, we have got LMI and IJK. So, I is the repeated index. So, we can then convert this term into the two terms that we have done just now, and we also have the dou by dou xm acting on two quantities. So, we have got the differentiation by parts that is coming here. So, we have got two terms on the left, two terms on the right. So, when we multiply, we must get totally 4 terms. So, there are the 4 terms that are written here. So, there are 4 terms here, and we are just blindly expanding the terms, and then we will see how we can make use of the properties of Kronecker delta to get rid of the indices. So, I am now illustrating that here. So, first let us see how the j is knocked off. Okay. So, I comes there, and then here j is knocked off, and so wherever j is there, I want to just knock it off. Okay. So, the other index of the Kronecker delta containing the j will be used to replace. So, the Kronecker delta that is used here is with L. So, that is the index that will come for f. Okay. And here it is m. So, that will be coming here, and here it is the L. So, that is becoming here, and here it is m. So, that is coming here. Okay. So, I have reduced now in each term, instead of 2 Kronecker deltas, now I have only 1 Kronecker delta, and then I have reduced the indices, and the indices have now modified. So, I do not have any more the j index in my expression. So, now we need to simplify further, and we use the same principle of Kronecker delta and simplify further. So, let us see how that is done. Okay. So, now you can see that we can now use the k to be knocked off. So, you could then see wherever k is matching. Okay. So, look at the k is matching, and then knock that out. Okay. So, you could then see that this implied that the m is a remaining index that is coming here, and here it is L that is coming here, here it is m that is coming here, and here that is L that is coming here. So, remaining things are untouched. So, you could see that we have successfully removed all the Kronecker deltas and modified the indices accordingly. Now, it is a matter of just recognizing the expression that we got in terms of the subscript notation. So, we could see that let me erase these and then show you the terms. So, you see that you have got the m matching both ways, which means that it must be a dot product. Okay. And you see that there is a m matching here. So, it must be the dot product here, and then again here, okay, and here. Okay. So, whenever you have got the subscripts matching, then you have got the dots that is coming in, and then whatever is a free subscript is basically the vector, and in our case what is a free subscript? It is a L. Okay. So, that would become the vector that is actually being mentioned here. So, every of these quantities, if you notice, you have got a dot product here, and that is a scalar, and then multiplied with a vector. So, it is a vector that is coming out. So, the entire expression can then be chosen. If you like to call that as p, then that vector p is basically p L, and then written in this kind of a form. Okay. So, you could see that such a long expression with just a few steps, differentiation by parts, using the Kronecker deltas and the properties of epsilons, we are able to now derive. Okay. So, here there are some more such derivations that I will not do it in the slide projection, but I will leave it to you to do it for your own practice. So, these do not involve any more concepts than what has been talked about till now. So, in other words, you should be able to do it yourself, and in the course website we will put up the detailed solution. So, you can verify the way you have derived with the solution that is provided to check whether you have got it right. You must be able to finish each of these within one page of the subscript notation derivations, and for you to see the value of this notation, you may try a part of the derivation using the vector components. I am sure that very soon you will realize that subscript notation is a way better way to derive and then practice the notation, so that we can make the algebra much smaller. Okay. So, with this we have had enough of practice of the subscript notation. So, the idea is to use this in many of the expressions that we are going to derive later on in transport phenomena. So, we will wind up the subscript notation session now. Okay. So, look at the website for the assignments for practicing more and for the solutions of the 3 exercises that have been given here.